Okay, let's jump back into an example here for multiple proportions. In this example, we're looking at Virginia Tech students investigated which vehicles came to a stop at a four-way stop. So they kind of staked out a four-way stop, and they just checked whether or not vehicles came to a stop or not. So that's a categorical variable, stop or not stop. And then what they paired that with is whether the vehicle arrived alone, whether the vehicle was in the lead of a group of vehicles, or whether the vehicle was following a group of vehicles. So, of course, the law is you must come to a complete stop at a stop sign. And the question is, does the way you arrived at a stop sign have an effect on whether you came to a complete stop or not? So, looking at the data, if they came by themselves, it looks like a complete stop was 85% of them. If they were in the lead of a group of cars, it looks like 90%. And if they were following a group of cars, then it looks like 77%. Okay, so this is our sample data. And you can see that so p hat would be 85.8 for p hat 1, p hat 2 would be 0.905, and p hat 3 would be 0.776. So these are your sample proportions, and they're not all the same. But are they different enough to conclude that there really is a difference in behavior, not just for these, 316 people, but among sort of all possible, the long run proportion of single vehicle drivers, do they stop? And the long run proportion of lead vehicle in a line of vehicles, do they stop? The long run proportion of drivers who are following, do they stop? Right? That's what we're wondering about. So sure, there's a difference here, but is this difference big enough to conclude that the long run proportions of stoppers are actually different? Okay, so we want to set up some hypotheses. So no association would mean that the long run proportions would be the same in each category. If there was no association between the variables how you arrived at the stop sign and whether you stopped. But if there is an association, then at least one of these would be different. And now we got to figure out, well, how unlikely is it to get the differences we saw in the data if, in fact, they all were the same? So we set up our hypothesis. Our null hypothesis is that there's no association between arrival pattern and whether they came to a stop. Or you can write this as the long run proportion of stopping is the same in each category. We could use the association language. There is an association between arrival pattern and coming to a stop, or the long run proportion of stopping is not the same for at least one of the categories. Now, it could be the case that two of them are the same and one of them is different. When we have multiple proportions, we do always want to say at least one of the categories. All right, if we can do this with symbols, pi single driver, pi lead of a pack, pi follower, those are the three true long run proportions, and those could either all be the same or at least one of them could be different. So that's how you would set up the null hypothesis with symbols, and the alternative hypothesis, we usually just write it out in words because putting in all the possible symbol combinations is a little bit pedantic. So then we go to the p hat. So p hat for a single driver, p hat for a leader, p hat for a follower, p hat for a single, p hat for a leader, p hat for a follower. So there's going to be three pairs of proportions. And when we subtract each one, we get three different numbers. And then the MAD statistic, as we saw in the last video, takes these three differences, makes them all positive, and then averages them. So you get the average of the positive differences, or the absolute value of the differences. And the bigger this number is, the more evidence we have against the null, because this is quantifying how different are these sample proportions from each other, at least on average. So, some of them were a little bit closer to each other, some were farther away. On average, they were this far away from each other. All right, and then we'll want to simulate. So, So in order to simulate, what we do is we do it the same way we did before with cards in the applet. So when we had two proportions, we just we knew what the sample proportions were, and then we just take all the cards and say, hey, these were successes, these were failures, and we just deal them into the two piles, and we say, well, what kind of proportions did we get by random chance? And then we look to see whether the difference we observed could have been had by random chance. And we're going to do the same kind of thing, but we'll need this multiple proportions applet instead of the two proportions. So I'm going to go down here into the stop sign data here, and it kind of has all the data, whether they came as a single driver, stopped yes or no, lead driver stopped yes or no, follower stopped yes or no. We'll copy this, and then we'll go to the multiple proportions applet. We'll clear this out, and then we'll paste it in. And you'll see it says explanatory response, and then we can click use data. And when we click use data, it turns it into this segmented bar graph. So we have the three of them, and it computes the MAD statistic for us, 0.086, okay? And then we can go over here to the shuffle options. So what shuffling is going to do is going to randomly deal out cards into three piles and see where the successes and failures go if we just randomly dealt them out. And then it computes the MAD statistic and puts a dot right there. If you do it again, computes the MAD statistic, puts a dot, do it again, randomizes MAD statistic. And if you do this a bunch of times, you'll see that the MAD statistics sort of have this pattern to it. Maybe we'll do it 100 times and see what we get. Okay, maybe another 100. Well, that's interesting. It appears it's not quite as bell curved as what we normally get, is it? It kind of has this shoe shape to it, kind of up and then down with a long tail to the right. And what's going on there is you'll notice 0, when you add up positive numbers, the only way to get 0 is if all the p-hats were the same. So it doesn't actually have a bell-shaped curve. It has, it's just this shoe shape, kind of, is what I like to call it. All right, so that's something, it's a regular pattern that always shows up, but it isn't a bell-shaped curve, so that's interesting. And what we want to know is the ones that were as extreme or more extreme as what we saw in the sample. What we saw in the sample was 0.086. And so we're going to count all the ones that are as extreme or more extreme than 0.086. And that happened about 86 out of 940 times. So our p-value is 0.09. So that doesn't feel like it's evidence against the null hypothesis, but it's not strong evidence. It could happen by random chance. We're sort of not quite into the tail yet. We're sort of on the edge of the tail there. Okay, so maybe you'd say we had some moderate evidence, but it's really not conclusive. Okay, so this is kind of showing you what the app looks like. It shows you the MAD statistic with the bar graphs. Then it shuffles it randomly and gets a MAD statistic, and then when you plot them out, you get that shape there. Okay. So then we talked about the strength of evidence. It is a two-sided alternative hypothesis because when we subtracted them and we made them positive, then that's really counting up both sides, but we're only looking at the right side of the null distribution. So it's a little bit confusing. It's a two-sided test, but when you go to the null distribution, you're only counting on one side. But it could be that one pie is bigger than the other pie. It could be the other pie is bigger than that pie. So it is sort of a two-sided test in that sense. And then the MAD statistic, of course, the bigger it is, the bigger the difference is. And we calculated the p-value by just counting how many times was it as extreme or more extreme. And that was 80 out of 1,000. I think we had maybe 90 out of 1,000 the last time. There's going to be some variation because it's a simulation. But 0.08, 0.09, that kind of a p-value. Not quite strong enough evidence. So in this case, we would say we had some evidence, but it wasn't strong evidence against the null. So we couldn't, it could be that the long run proportions really are different, but we did not have evidence for that, or we didn't have strong evidence for that. So it's possible or plausible that the proportions of stoppers are the same for all three categories. Okay. Do the results generalize? Well, it's one particular intersection, so you might want to be careful about generalizing to all drivers at all intersections, because the data was very specific to one place. Cause and effect. So this is interesting. It was an observational study. They just sort of came up and looked. They didn't randomly assign drivers to be in one of the different situations. So it wasn't a randomized experiment. So you'd want to be careful when you said cause and effect, because it was just an observational study in this case. They just sort of sat at a thing and saw what happened. If you had stronger evidence, you could follow up with pairwise tests to see which proportions were different. Maybe you could conclude that one proportion was for sure different from the others, but you couldn't conclude that the other two were different. And you can sort of follow up with basically just comparing this one to this one, or this one to this one, or this one to this one. You can kind of do individual two proportion tests comparing different ones.